Okay, so let's get started. A minute or so early, but there's a lot of material I want to cover for you for this class, and that's also for the lab. So today we are going to switch gears and talk about a different topic, which is concurrency in distributed systems. So the first part of this lecture will give you a quick refresher on threads and concurrency. The standard assumption that we make for this class is that you at least seen what threads are in an undergrad OS class, which you remember is something we assume as the background. But some of you may not have taken that class, and we recognize that. So I'm going to give a quick refresher on what threads are, or if you've not used them, this is a good way to bring yourself back up to speed, because that's what you're going to use for your lab. Okay, and then the next part will be concurrency model, and towards the end we'll see how operating systems can schedule threads. Okay, so it's going to be the start of our material on scheduling, starting with thread scheduling. Okay, then we'll talk about cluster scheduling and whatnot in a future class. Okay, so with that, let's get started. So let's try to understand what is a thread. Okay, so first you need to understand what a process is. Okay, a process is simply an executing program. Okay, so a process will have some memory allocated to it. Okay, the memory will have a stack and a heap, and it will also have the code of the program loaded in it. Okay, and when you process executes, the code is going to execute, and essentially you have one thread of control through a sparse process. Okay, so essentially the program is executing instructions, and it's executing them sequentially. Okay, this sequence of execution is called a flow of control. That's the control flow through the program. That's how the code is essentially executing. Okay, now in a traditional process, there is one execution flow. There's one thread of control that goes through that entire process. Okay, now when you take this concept and you generalize it, you get what is called a multi-threaded process. Okay, and within multi-threaded process there are multiple threads. Okay, so what is a thread? Think of a thread as a lightweight process, which is a flow of control through an address space. The address space is the memory of the process. Okay, the process has multiple threads. They all share that memory. Okay, remember, each process has a different memory space allocated to it. So each process has an address space, and in this case, you will have multiple threads that are executing concurrently through that address space. In other words, there are multiple flows of control through that address space, and so you should think about there's one thread that's executing some instruction, maybe it's in one function, and there's concurrently another thread that's executing some other part of that process, and a third thread that's executing yet another part of that process. So you have your code of that process, code segment is shared by all of the threads, but different threads are executing different parts of that code that you have written for this process, all concurrently. Okay, so that's essentially the concept of a thread. I'm going to show some examples. Now, if you have multiple cores on your machine, each of these threads could execute on a separate core, and you get what is called true parallelism. So essentially, different parts of the program are executing in parallel on different cores of your machine. Okay, even if you have a single core, you still get concurrency. Okay, where if you switch between threads, thread one executes some part, then you switch to another thread that executes some other part, and so on. So you get concurrency, but not parallelism. When you have multiple cores, you get concurrency and parallelism. Okay, so that's the concept. And whenever you have threads, you have to remember that whenever these threads access anything that is shared, any data structure that is shared, you are going to need to use synchronization. Okay, so when you write multi-threaded code, you not only need to understand how to create threads, how to use threads, how to terminate threads, you also need to understand the concept of a lock or a semaphore or monitors. These are all synchronization primitives, and you need to use them whenever these threads are accessing anything that is shared. Okay, so threads, synchronization are all related concepts. Okay, today I'm not going to talk about synchronization. In fact, we will not talk about them at all. I'm assuming that you will at least know how to use a lock when you use threads. I'm going to only talk about how threads work and so on. Okay, All right. So here's another picture of what I was just saying. So this thing in the middle is the memory space of a process. A process will have multiple segments. The memory where you store variables, those segments are either called the heap and the stack. Okay? And then there is a code segment, which is where the code of that process is going to reside. Okay? So the middle thing here is essentially the code segment. Okay? Now, each thread that you create within that process, okay, will execute some part of this code, okay, concurrently with other threads. So there are three example threads here. You see that thread 1 is executing some instruction there, wherever that arrow point. Thread 2 is executing an instruction where this other arrow points, and so on. Okay? Now each thread gets its own stack, okay, because that thread can call other functions. You have to push those variables on the stack and so on. So you will see that there are 3 shaded boxes here. So those correspond to the stack of each of the thread. Okay? Each thread also gets its own copy of the program counter and registers, because the program counter is going to tell you what instruction is being executed. So each thread has its own copy of registers, it has its own copy of the stack, but everything else is shared. Okay? The code segment is going to be shared. Okay? This is a picture at a very high level you want to keep in mind, but we'll talk about now how to create threads and so on. Okay? Is this clear so far? Okay. So why would you use threads? As our systems have started getting more and more cores, okay, even your phone is going to have 4 or 8 cores now. Okay, that was not the case some time ago, where machines would barely have, not barely, only have 1 CPU, but never more than 1 core on that CPU. Now we are in a world of multi-core systems. Okay, your laptops have many cores, your tablets have many cores, phones have many cores. So this gives you an advantage where if your application is written using multiple threads, you can take advantage of these cores. Okay? If you have a single threaded process, a traditional process, that can execute only 1 core. Okay? So all your other cores cannot be used by that process when it's executing on 1. But if you have multiple threads, you can take advantage of more than 1 core and get parallelism. Okay? You can basically use that to even increase performance of your application. Okay? So that's one reason, as your multi-core, multi-processor system, threaded application can take advantage of the hardware. Okay? The other is switching between processes is a much more heavyweight operation than switching between threads of the same process. Okay? The reason is the threads of the same process are going to share the address space. Okay? So you just have to change the program counter and the registers, and you can start executing another process. You don't have to swap out any memory management information or anything like that, because it's the same process. Okay? But if you switch from one process to another, you have to save all of that processor's state in the operating system's memory. Okay? And you have to load the next processor's state that you want to execute. That's a much more heavyweight operation. That's called a context switch. Okay? Context switching is more expensive for processes. It's lighter weight for threads. Okay? So if you have lots of threads in your application and you're just switching between threads of that application, that's a much more lighter weight context switch. Okay? So that saves you some overhead as well. Okay? And as I said, you can actually get true parallelism. Yes, question.
What's the distinction between the thread sharing address and each thread having its own stack?
Okay, question is, what is the distinction between each process sharing address spaces and yet having its own stack? The first thing is, when I say an address space, that thread has access to the entire memory of the process. Okay? Now, you may have your own stack, but you still can actually address any part of your memory, including anything that belongs to another process. Another thread. Okay? Because the entire address space is visible to you. Okay? So you have your stack, which that thread is going to use to execute, but everything else in that address space is accessible to you because it's just a memory address. You can have pointers that can point to any part of your address space. So it's still shared. Yeah? But while executing, you still have your own stack. Okay? Any other questions here? Okay, so let's look at some example. Okay, very simple example here. It's a Python code. You have essentially this is a single-threaded process, a single-threaded program. Okay, no threads in here. So it is just a task where you start something, you print a message, you sleep, and you print done. Okay, so you call that function twice. Okay, so essentially this is sequential execution. There's no threads here. Okay, so your main program is going to go call that task function. Okay, and then once that, so that is going to go sleep for a while, then print those messages, then it's going to call that function again. Okay, so in the timeline here, you will see the task is executing. Okay, then it's going to sleep for 1 second. Then you essentially it's going to print that thing was done, and then another task is going to another function invocation or task is going to take. Okay, simple sequential execution, no threads yet. Okay, now let's see what you can do with the thread. Okay, so now we want to call this task function twice, but we are going to call them in 2 separate threads, not from the main program. Okay, like we did in the previous example. So it's the same task function at the top. Okay, so you're going to create thread T1 and T2, and each of them is going to be asked to execute the task function. Okay, now your execution is going to be concurrent. Okay, because you're going to start these threads and you're going to get concurrent execution. So to some degree, what's going to happen depends on exactly how the CPU is going to schedule these threads. But here is one execution sequence. There couldn't be other because the interleaving may be different. Okay, so the first thread is going to start executing and is essentially going to go into the task function. Okay, it's going to print and then it's going to sleep. Okay, when it sleeps, it becomes idle. Okay, this basically means that the CPU has nothing to execute, so that CPU is going to now switch to something else. In this case, we'll assume that it's switching to the second thread because that thread is ready to execute. So that task is going to execute. Okay, the first task function is still sleeping. Okay, so then it's basically we're going to sleep, and then what is not shown here is each of those task functions will resume and do the final print, and then you will be done. Okay, so you essentially got some interleaving here. Is this clear? Yes, question.
Running this code counts as its own thread?
Does running the code count as its own thread? Okay, so typically what happens is when you start the process, there is always a thread which is going to be executing main. Okay, so you have a main thread, okay, which is not shown here, by the way. And then that main function is going to invoke, call these thread methods which create 2 new threads. And then you basically started executing them, and you'll see that the main is just waiting. It doesn't do anything. It just creates the thread, it starts them, and it waits. But it could also do other things, in which case there are 3 threads in this process. Okay, the main and 2 additional threads. Other questions? Okay, what is the question is what is the join function doing at the end? Join simply means wait until the thread is done. Okay, so join just says wait for the thread to complete. So it just waits for the first thread to complete, it waits for the second thread to come. So the main function is not doing anything. Okay? Yes. Question is what happens if the stack of a process is full? So the stack of a thread is full. So essentially that the address space of a process is very large. You can fill up the stack if you just start putting a lot of stuff out. I mean, if you just do a recursive call, an infinite recursion, eventually you'll run out of stack space. Okay, so if you do that, then you'll run out of stack space, and then the thread will not be able to execute. You'll get a memory error. Okay? Like any other, you don't need a thread for that. You can just write an infinite recursion. Your function keeps calling itself. After some number of invocation, it will run out of memory. The question is if the thread has an error, is the whole process terminated? That need not be the case. That depends on the error. If you do something bad like illegal memory access, the whole process gets terminated. But if the thread just ran into an error, it can just exit, and then the main function can essentially treat that as an exception. Okay, so it depends on the type of the error. Yes, question. Okay. Okay. Question is it better to have threads doing short operations, or should their threads do long operations? So we'll come to thread pools in just a few slides. we'll talk about exactly this concept and you will understand the difference. Okay? The answer is it depends. There is no right answer to that question. Depends on what you want to do, how much overhead you want to pay. Okay? The pay of creating threads, deleting threads, and managing threads. Okay? But we'll address that question specifically in the context of how to write a server application. Should you have long-running threads or short-running threads in a server? And then you will get the answer to whatever you ask. Let me wait on that. Okay? Yes. Okay, is the join method like a blocking call? So join is a blocking call that waits for the thread to come, not the process, waiting for the thread. Yeah, the main thread is waiting for its two child threads to complete. So T1.join and T2 join. Okay. Yeah, so question is, if you have code after the join, will it continue? So the main function can continue. Here it exits. Right, so you can have other code after it. In this case, it just blocked for its child threads to complete it. Yes. Okay, that's a good question. Question: why are they not running simultaneously? Are we assuming single core? This is right at this point, single core execution. Okay, if you had two cores, you could have one task running on one core, another task running on another core. So this is single core concurrency, not true parallelism at the moment. Okay, so let's talk about what this all gives us. So you have, at this point, we talked about a single threaded process, traditional process, no threads. Okay, so they make blocking calls. There is no concurrency or of any sort, no parallelism. If you have multiple cores, a single threaded process can only run on one core. It cannot take advantage of anything else. Okay, then we talked, so we'll come to finite state machine. You talked about multi-threaded process. Okay, they also make blocking calls. Okay, when you do print and all of this, these are blocking calls. Okay, so still making blocking calls, but you can get both concurrency and parallelism if you have multiple cores. Okay, because now your threads can actually run in parallel. Okay, there is a model in between which is called finite state machine or event based. Okay, this one uses non-blocking calls to get concurrency. Okay, so a single threaded process, but all calls are non-blocking. So you don't wait for anything. Okay, you just make the call, you continue execution. Okay, this requires you to use something called asynchronous IO. Okay, we'll see some examples later in this class of how to use asynchronous IO. Okay, it is used for high performance applications in many cases, where you use those calls to reduce overhead of creating lots of threads. Okay, excuse me. So threads are going to retain this concept of a sequential process where each thread is having multiple sequential execution control rules. Okay? And you use standard blocking calls. You don't need to worry about doing anything asynchronously, and yet you get parallelism. Okay? So from a software engineering perspective, writing multi-threaded code allows you to take full advantage of the hardware on your machines. Applications are easier to structure as a collection of thread. Each thread can do a certain task in your process. Okay, so you already modularized your code. Okay, if that code can be parallelized, you can then say these set of functions can be handled by this thread, some other set of functions, another thread, and so on. So you can essentially get that modularity. Okay? And threads can perform independent tasks. They can also perform dependent tasks, but you can use them to do independent tasks. Okay, so we'll come to asynchronous IO. So far, we only looked at single-threaded and multi-threaded process. So let's look at some examples. Okay, first one is browsers. Okay, we'll look at browser as a client and a web server. Okay, so where would you use thread in a web browser? Okay, you all know what a web browser is, right? So how would you use threads in? I'm sorry. Each tab could be a thread. So you could have different tabs that serve different threads. Then you have to think about what is happening in one tab. Okay, so you say you click on a link. Okay, you could have some thread that is actually responsible for the network communication. Go fetch the page. Okay, and the page comes. Another thread could be rendering the page. It's actually parsing the HTML and trying to render it. Okay, maybe there are embedded images in your HTML page. You can have each thread and go and fetch an image. And when the image appears on your browser, you can then render them. Okay? So various tasks that you can think of can be assigned to threads within a browser. And if you look at any modern browser, whether it's Chrome, Edge, Safari, they will all be multi-threaded. They will have 20 or 30 threads. You can actually, on a Mac, for example, go to activity and then look for the process, and it'll show you how many threads are actually part of that process. So you'll see most of these processes now tend to be multi-threaded, including browsers. Okay. So, and then if you have ads in them, you can have other threads fetching ads and all this kind of stuff. Okay. That's an example of how you can take a browser and have different threads in it, having them do different activities. Okay. Now here's a server. Why would you need threads in a server? Okay, remember that a server application can service multiple clients. Okay. So that should tell you that that's a good way to use threads. So you essentially have threads that serve each client. So each request comes in, you can have a thread that actually services that request. So multiple requests from multiple clients arrive, okay, you can have different threads serving them concurrently, okay, rather than doing things sequentially, which will make other requests wait. Okay, so here, this is essentially a picture, a very standard picture of how servers work. So there is always a dispatcher thread. Okay, that's a thread that's going to wait and listen for requests. Okay, and then here you have 3 worker threads in these boxes. Okay, so dispatcher thread waits for a request comes, it will assign it to one of these threads. Okay, so essentially you take an idle thread and you assign them requests, and when the request is done, the thread becomes idle again, and then the dispatcher will continue. So essentially all the servers sit in a loop waiting for requests and then assigning requests to threads. Okay, is that clear? And we'll see several ways to implement this, which will be directly relevant to what you're going to also do in your lab. Okay, yes.
Is single-threaded and sequential?
Question is, a single-threaded and sequential execution the same thing? They are not the same thing, they're related. Single thread means that your process has a single flow of control. Okay? Each thread, whether it's one thread in a process or multiple threads, executes code sequentially. Okay, so sequential execution just means you're stepping through statements. Of course, you can have if statements and loops, but you're still doing sequential execution. Okay, anything else? Okay, so that's your multi-threaded server example, and we'll now see in a short while how to write this. Okay, so we have finished a very quick introduction to threads. Okay, if you're not programmed with it, you will program with it soon, and we'll give you examples of how to do it. Okay, but there are some ideas you need to know of how, because our assignments are all client server assignments. So it's good to know how to write a server application. Okay, so this is going to be a set of slides that tell you how to write server application using different threading models, different concurrency models. Okay, so we're going to look at concurrency for server-side application. So first thing to realize is all server applications are going to look like this. Okay, they will have an infinite loop. Okay, in that infinite loop, you're going to wait for an incoming request. You might be listening on a socket connection. We looked at that last time, or you may be waiting for an RPC call to arrive. Okay, doesn't matter what the communication method. You just wait for a request. A request comes in, you process that request. Okay, and this is called an event loop. And now the question is, how are we going to use threads to do this process? Okay, but this is our basic structure of any server application. You wait for a network request, you process request. Okay, so let's see how to write event loop. So we'll start with our sequential server. This is basically the most trivial form of writing a server. So you essentially wait in a while loop and wait for a request to arrive in the queue. Okay, the queue may be a socket queue, or it could be an RPC request coming in. Okay, so you wait for a request. Okay, and then once you've gotten a request, you process the request. Okay, there is no concurrency here. While you process the request, some more requests may arrive. They'll wait in the queue because there's no threads here. Okay, so you're just waiting for the request processing to finish, and then you'll go back to the while loop. Is there any request in the queue? If you pull it out, you process. Okay, essentially you're processing requests sequentially. Okay, very simple way to write a server. Okay, disadvantage is your request might start queuing. If multiple requests come, they have to wait for all the requests before you to finish, before you can be processed. So the delay that the user or the application that sent that request is going to be high. because there are higher waiting times at the server. Okay, so this increases what is called waiting time or queuing delay, so the response time of your server will be slow. Okay, so you don't want to do this if you can avoid it. So you want to make the server multi-threaded. Okay, this is the event loop of a multi-threaded server, not very different. Okay, so you wait for a request. Okay, so you pull a request from the queue. Okay, in this case, you are going to create a new thread to handle the request. So you say create thread, okay, and then you essentially say process the request. Okay, so every time a request comes, you are going to start a new thread. You are going to hand the request to that thread. Okay, the request is going to process that thread, send back a reply, and then the thread will terminate. Okay, the lifetime of a thread is the lifetime of processing that request. Okay, this is what was being asked earlier. These are short-lived threads. So we essentially create a thread, process the request, the thread is gone. Okay, this is called a thread per request model. You spawn a new thread every time a request comes. Okay, very simple. Okay, newly arriving requests never have to wait. So as soon as a request comes, you create a thread and you hand it off. If lots of requests comes, you create lots of threads and they all process them in concurrently. Okay, so always you can assign our request. There's no waiting because you can create a thread and hand it over the request. Okay, now the disadvantage is there is frequent creation and deletion of threads. Okay, because you're creating threads rapidly and then they just serve a small request and the thread goes up. Okay, there is an overhead we pay for creating and deleting threads. Okay, it's not high, it's not as much as creating an entire process, but there is still an overhead. Okay, so in this model, although it's very simple, okay, we are going to pay the cost of frequent thread creation and deletions. Okay, but this is called a thread per request model. Okay, all right. So what can we do to avoid this thread creation and deletion? We are going to use a concept called a thread pool. Okay, we will pre-spawn a set of threads. Okay, and that will be part of your thread pool. So we'll create n threads when the server starts up. Okay, those n threads are going to wait for requests. Okay, so here is our event loop. So first you create the thread pool with a size. Okay, the size says how many threads to create in the server. So these are all going to be part of your thread pool. Okay, all right. So now you wait for a request. Request comes in, you go to the thread pool and say, is there an idle thread? Thread that's not doing anything, not actively servicing a request. If so, you assign the request to that thread. Okay, and then that's the thread will service that request and it will go back to the thread pool as idle. Okay, so you're not creating new threads. You just created a set of static threads and then you started serving them. Is that clear what is happening? So this is called a thread pool model. So you pre-spawn a set of thread. There's a dispatcher thread. That's this main loop. Okay? And you're just assigning work to these threads in the pool. Okay, yes, question.
When a process is done, that particular thread is idle.
Okay, question is if a process is done, can you assign the thread next? So first of all, this is one process. Okay, there is no new process. You're talking perhaps of request. Okay, the request is being processed and you sent a reply. That thread is going to go back to the thread pool as an idle thread. Okay, so you essentially look for idle threads and you pick one of them and you give it a task. Okay, when the thread is done, it's going to go back to being idle. So threads can either be idle or actively processing a request. For processing a request, you are not asked to process anything new until you are done. If you're idle, you can be asked to process another request. Yes, question.
How do you get the thread that a particular thread is idle? And what if there are no threads?
Okay, how do we know that a thread is idle? So idle threads will be part of the thread pool. That's how you implement a thread pool. Right? You are going to implement one. So you will have to figure out how the thread is idle. But that's not hard because you can just add your thread. If you're an idle thread, you can simply add your ID to an array or a queue saying I'm an idle thread. So if you can just pull the first ID from the queue and say this is idle thread and then you assign it somewhere. Okay, and the thread becomes idle again, it needs to re-put its ID back in. So there'll be some mechanism by which you need to know a thread is idle or not. You can use some simple mechanisms like that. Okay? That's the first question. The second question is what happens if the thread pool is full? That's the question here. I'm going to come to that. Okay? So the first advantage of this process, thread pool model, is that it is going to avoid our thread creation and deletion overhead that we had in the thread per request model. Okay? Because you created them once, you don't create, you just reuse the thread, you're not creating new threads. Okay? But there's a disadvantage because you created n threads. Okay? N is chosen at startup time. Okay? What if n plus 1 requests arrive at the same time? What is going to happen then? Okay, you will get queued. So first n requests are going to get assigned to the n threads because initially all threads arrive. Okay? Now all threads are busy. Okay? Another request comes. Okay? You basically look for an idle thread. There isn't any. So that request has to wait until one of the thread finishes its processing, and then you get assigned. Okay? So in this case, your request waiting time can be non-zero if there is a burst of arrivals and your thread pool is all busy. In the thread per request model, that was not the case because you could always create a new thread. Doesn't matter how many requests are coming in at the same time. Each thread gets a new, each request gets a new thread. Okay, so there was no problem. Here you pre-spawned n. If n is very large, that condition may never arise. Okay, you can say I'm going to create a very large thread pool. Yeah, you may never get that many concurrent requests, so there is no waiting. Okay, but if you create a very large thread pool, your memory size of the process will also be high because each thread has to have its own stack and so on. Okay, so you are going to pay in terms of memory cost. So you should not just make an arbitrarily large thread pool. The thread pool has to be chosen carefully based on how many requests you expect to arrive at the same time. If you don't know that number well, you may have waiting. Okay, so what can you do in this case if you don't want to pre-spawn a very large number of threads? Your question? Okay, question is, if you have a thread pool of n threads, is there an n plus first thread, which is the main thread, or is that part of the thread pool? So in this case, the main thread is a thread. Okay? Then you create n more. So there's n plus 1 threads in your program, your process. Okay? Question. Question is the main thread the dispatcher? Yes, in this case, the main thread is sitting in a while loop, so it is the dispatch. Anything that's processing the event loop, which is this while loop, is the dispatcher. In this case, it's the main program. Okay, so it's the thread that you start with. Anything else? Okay. So choice of n will govern the performance of your server. If you make it too small and too many requests come in at the same time, they'll be waiting. If you make it too large, you will have high memory cost even though you don't need that many. So you have to choose it carefully. Okay. Now there's another way where you don't need to choose it very carefully. You can make the thread pool size variable. Okay. This is called dynamic thread pool. Okay. So in this case, what is going to happen? There's no code here, but there's the logic of how the thread pool size is varied. So the optimal size of the thread pool at any time depends on the request arrival rate at that time. Okay? You can assume that the arrival rate might change. Sometimes there are few requests arriving, there may be peak hours, there are more requests come into your server and so on. Okay? So the arrival rate or the load of the server workload is not going to be static. It will vary over time. Okay? So we want to vary the thread pool, okay, based on the workload. There are more requests coming, we make the thread pool bigger. There are fewer requests coming, we make it smaller. Okay? That way we don't need to ever worry about how do I pick the right n. I adjust n based on whatever load the server sees. Okay? So how will we do this? We start initially with n threads. Can we monitor the number of idle threads? Okay? The thread pool can at any time figure out how many threads are idle and how many are in use. Okay? If you see that the number of idle threads goes below a low threshold, you have a low threshold. If it falls below that low threshold, you say that more threads are being used, so I'm going to spawn some new threads. So I always have some threads on standby. Okay? So I made the thread pool bigger. Okay? And then if you see that the number of idle threads crosses some high threshold, okay, which is different from your low threshold, you say there are too many threads idle. Okay, maybe there's not enough work coming into the server, so we'll terminate some threads and shrink the thread. Okay, so you keep the number of threads in the thread pool somewhere between your low and high threshold, the idle threads, not the total number of threads. Okay. Yes, question. Okay, question is, do this low and high threshold, are they constant or do they vary? So that we are not going to vary. That's the only thing we'll configure at startup. Okay, so we'll assume that there is high threshold above which you create and low threshold. So that can create more threads for you depending on what is happening in the system. Okay, modern web servers are going to use a dynamic thread pool because there's no real way when you write the code that you actually know when it's deployed in some application how many requests are going to come. That's only known at runtime. So you make a thread pool dynamic so that it will adjust to whatever runtime behavior the server sees. Is this clear? Okay. Okay. So I should mention that there is one more model. Maybe I can come back to that. I'll come back to the other model, but let's talk about the asynchronous event. Okay, so everything we saw so far was a multi-threaded server, okay, that had an event loop. Each thread is doing synchronous IO. They're making blocking calls. Okay, you can write servers that are concurrent but have no threads in them other than the main thread. There's only one thread, yet you have concurrency. Okay, the only way you do this is through using non-blocking IO. Okay, so essentially what is going to happen is your main thread is executing, it makes a call. If that's a blocking call, normally you use a non-blocking version of that call, and then the call goes off and gets processed, and then the main threads then will switch to something else. Okay, and then you'll start processing some other part of the function, and so it will jump back and forth and process different parts of the code, but never stop for IO. Okay, all IOs are blocking calls, for example. Okay, so always use non-blocking IO instead of blocking IO, and then whenever the IO is being processed in the background, you start processing something else. Okay, so you will get concurrency by just using one thread because you are using non-blocking IO in this case. Now, here's an example of how this is going to work. So you essentially, this is Python. So if you're using asynchronous IO, you have to add the async keyword in front of that function that makes the function essentially compatible with asynchronous IO. Okay, so what is going to happen here is you will use an asynchronous version of sleep. Okay, so you're going to make that thing sleep, but use an asynchronous sleep, which means that this is not going to be blocking for that function. Normally, you would essentially wait in that for a second and be making a non-blocking version. So essentially, your main function can call the count function 3 times. Okay, and if you had called them 3 times sequentially, you have to wait for each one to finish before you execute the next one. Okay, here, as soon as the first function does any IO, which is in this case sleep, you will basically start executing the next one instead of blocking them. So essentially, that function will return back to the main. The main will then continue and execute the next count. You will essentially do this and you'll continue and so on. Okay, so essentially that's your asynchronous version. Here is the synchronous version where you just use regular sleep and you call it 3 times. So in this case, you will just execute sleep, execute print, then you go execute the next time, the next iteration of count and so on and so forth. Okay, yes, question.
What about the synchronous sleep function causes the next thread to run?
What about the asynchronous sleep causes the next thread to run? So there's first of all only one thread. There's not multiple threads. Okay, so the whole point about asynchronous event loops is that you are doing what a multi-threaded program does with a single-threaded program. Okay, so this is a single-threaded program that has concurrency. The way it has concurrency is you take all the blocking operations of a normal single-threaded program, make them non-blocking. So while that blocking operation is actually executing in the background, you can do something else. Okay? A normal program would basically execute block on IO, execute block on IO. So every time you block, you are not doing anything. So if you replace that with a non-blocking call, you still execute that IO, but you don't block, so you can go execute something else. That's the main idea. The single-threaded process. You are getting concurrency. Okay? So the way you have to do this is you have to take all your IO operations and make them asynchronous. Okay. Normally you should have made that print also asynchronous because that's technically IO, but we didn't do that here. We only made the sleep asynchronous. Okay. So in this case, sleep will be a non-blocking sleep, which means that count will sleep, but you will essentially return the thread of control back to the main, go back to the main function. It will execute, in this case, the second iteration of count and so on. Okay. Next question.
After that line where you have wait asynchronous, does the control flow to the next? That's like a fire and forget sort of thing that 2 gets printed first and then the control flow is returned back to the second one.
Yeah, question is what happens when you have the await and sleep? Is it going to continue execution or is going to do something else? In this case, as soon as you do non-blocking version of IO, you are going to go back to the async IO gather and execute something else. So it has to actually sleep before it executes, but you are not going to make the thread sleep. Think of it as a function is sleeping, okay? But the thread has gone back to do something else. When the function is done sleeping, it will come back and resume execution because it's not done here, right? So this function is not completed. So when that 1 second passes, you can come back here and continue execution. If some other thread now decides to sleep, you switch back and continue. So you're switching back and forth just as a thread multiplexing would do. A CPU scheduler would do that for you automatically. Here you are doing this inside the process. Yes.
When the first count is done sleeping, does it take back control or does it have to wait for control?
Okay, when the first count is done sleeping, does it take back control or does it have to wait? In this case, you will have to wait for whatever is being executed for that to do non-blocking IO and yield control back to this process. So then you can switch back. Okay. Okay. So the thing to keep in mind is here, the way the control flow is going to go is not clear because it will depend on what asynchronous sleep does. And so you're switching back and forth. So asynchronous program is much harder to write and understand. Okay? And if you've done any event programming, that's also very similar because another event fires, you go into an event handler, you stop doing whatever you're doing, you go into an event handler. That's also like asynchronous programming because you're switching back and forth from one part of your code to some other part of it. But if you write this as a multi-threaded program, it's much easier because you could have just essentially had that function created 3 threads and just had them execute. And it looks like you're executing a normal program. Here you have to put asynchronous calls. You are going to switch back and forth. So how the program is going to execute if there is a bug is much harder to figure out. So, but it's more efficient because there is no thread switching. Okay? Because you're not even switching between threads. There's only one thread that keeps executing. It's just executing some other part of the program. Okay? So all the thread context switch overhead is also gone. So it is far more efficient than a multi-threaded process. There's a question there. Yes. Okay, question is what is it that does the asynchronous IO for us? So you have to implement a new IO library, okay, that is designed to do asynchronous calls. Okay, so you essentially this requires the whoever has written the library or the programming language runtime to give you asynchronous versions of blocking calls. Okay, so you will call asynchronous IO. You can call asynchronous file read. That read will not block until the data comes back from your file. You will just continue executing something else. And once the data comes, you will have an interrupt or you'll have a signal saying the read is completed. Then you go back and process. Yeah, so it's done inside the runtime. You are not doing this, right? So you have to have these versions in your favorite programming language. Otherwise, you cannot do this. Okay, yes, question.
Who is calling the whatever different thread voice?
So I'm not following the question. So you said async is going to make calls. You're going to have asynchronous operation that is going to transfer control flow to some other function. Okay, so
we did call await sleep. Then we
move on to another count.
Yes.
And when sleep has completed, so that it is done to the current. So who is actually monitoring?
Question is, who is monitoring that an asynchronous IO has finished? That's the asynchronous IO library has to figure this out. So it has to figure out what asynchronous IOs are in operation. Once they're done, that function becomes runnable again. So you can resume execution, right? So that's all handled by the asynchronous IO library. You're not doing anything as a program. That's handled internally. Question, is that a different thread? There is only one thread here. That's the main thread. Okay? But the library can tell you what to execute in this case. Okay. Okay. So here is actually a longer program that does all of this. It's the same thing what I showed. I'm not going to go into all of the detail. So you have to essentially use asynchronous calls. And essentially, the way you are going to do this, you have to have an await and async pair. Okay? As we saw, essentially there is a so that's your event loop. And if you go back to the previous thing, so you see that there is an await here, okay, and then which is going to wait, and then there is a then async that allows you to synchronize. Okay? So that's your async dot get event loop and so on. Okay, so you have the function has to have an async that makes it an asynchronous function, and inside if you do await, then you are going to essentially yield and then go back to something else. Right? So you have to have these two pairs so you can switch from an await to another async function and back and forth. So that's how you can take standard Python and turn it into an asynchronous IO based program. Okay, gets more complicated, but you can essentially get better performance if you can write that program well. This question is. The question is, if you skip the await keyword, then what happens? If you skip the await keyword, then you're doing synchronous calls. Then your entire thread will block. Right? You can, of course, have synchronous calls in an asynchronous program, but you're not going to get any concurrency at that point because your whole program is blocked. So if you do read in the standard program, it's blocked. It's not going to run anything else until the read finishes. So if you use synchronous IO within a program like this, you will cause the whole program to block. And then once that IO finishes, then it will resume execution. And then there's other asynchronous IO, you can switch back and forth. Okay, yes.
Does this only reduce runtime significantly when function that has a wait on it takes a significant amount of time?
Question is, does it reduce the runtime significantly when the function has an async? Is that your question?
Just a print statement. It doesn't seem like it would cause any real speed up. But the speed up when the thing that you're awaiting takes a while.
Okay, question is, where is the speed up? So the way you want to think about it is asynchronous IO allows you to have a single threaded program behave like it is a multi-threaded. Okay, so if you had written multiple threads and they were doing different things, right? If one thread blocks, you think about it, let's say there are two threads. The first thread is doing something and it makes a blocking call. Okay? What happens in this case is the operating system says that thread is blocked, let's run another thread, and it picks the other thread to run. So the OS has made the switch. Right? And then the other thread runs while this thread is blocked. And when this thread is done, you'll move back and you'll continue. You're doing that inside the program without the scheduler doing it. So you make an asynchronous call. Okay, so that you make a non-blocking call that allows you to then switch to something else and execute. This is what the OS would have done if you had actually had threads in your program. You emulated that behavior using asynchronous calls. Okay? So essentially, this is a way, it's not a way to speed up anything. It's a way to use a single threaded process, behave as if you have threads. So you're essentially getting concurrency out of a single threaded process, which if you had blocking calls, you will never get any concurrency. You just block. Okay. Any other questions here? Okay, so the lablet that we gave actually has a asynchronous IO example. Okay, but you don't have to worry about doing that in the lab because the lab is all threaded and synchronous program. Okay, but something you should know it exists, and there is ways to write servers using asynchronous IO. Okay, there's one more model I want to talk about. Then we'll talk about some other example. That's the processor pool model. Okay? A processor pool model is like a multi-process server. Just as you have a multi-threaded server where the server has multiple threads, some are worker threads and some are dispatcher thread, you can do the same thing at a process level. Okay? You can have your application as a collection of n processes. Okay? There's a dispatcher process and a set of worker processes. The dispatcher process listens for network requests, and then it's going to hand that request to another process, not a thread within this process. It's a completely different process. Okay? And then that process goes off, finishes processing, and then it hands back the response, and it goes back to the idle pool. So everything we talked about in a thread pool model also works in a process pool model. Okay? Now, the bigger difference is here, when you hand off a request to another process, you have to do a context switch and switch to that process. That's more expensive. Okay? Because I said context switching between processes is more expensive than switching between threads of the same process. Okay? So if you have a process pool server, okay, when you switch between processes of that server that are executing requests, you pay a higher context switch overhead. Okay? But it gives you better isolation properties. Okay? If one process of that process pool does something bad and crashes, okay, the rest of the processes are still intact because they're independent processes. Okay? Your server as a whole will continue to run. If you have multi-threaded server and one thread does something illegal, okay, like tries to access memory region it's not supposed to or something like that, okay, the OS will terminate the entire process. Like if you do a segmentation fault, the whole process is gone. The server will basically get terminated. Okay? So this has better isolation across workers. Okay? And process crashes only impact the request, not the application. Okay? Whereas in the multi-threaded case, it's the opposite. Okay? Disadvantage is switching is more heavyweight. Okay? Now, if you look at applications like the Apache web server, a very popular web server that is open source, used for hosting all kinds of websites, okay? It actually uses a process pool model. Okay, you have a master process, your set of child processes, and then you can essentially hand requests. Okay? It also supports multi-threading. Okay? You can also have a multi-threaded version of Apache, but by default, it has always used a process pool model. That's how it started. Okay? And everything we said in the threaded case, static pool size, dynamic pool size, it also applicable for a process pool. Okay, because you can decide what the pool size is, change it over time, etc. Okay. So we looked at three architecture, right? We looked at sequential servers, process one request at a time. Okay, and essentially the only way you are going to get concurrency there is if you use asynchronous IO. Otherwise, it's going to do pure sequential processing. Okay, then if you want multi-threaded servers, you're essentially going to be either using a process pool model or a thread pool model or a thread per request model or a process per request model. One of these things have to be used. Okay, so this is going to give us a whole set of models, pure sequential, okay, just simple sequential processing, event based. That's one thread but concurrency. So this has no concurrency whatsoever. This has one thread but has concurrency because you're using asynchronous IO. Your thread based, okay, where you just have threads with standard blocking call, and your process based. Okay? You have multiple processes that make blocking call. Okay? So you can write your servers in any of these models. Okay? So you can say which one has more efficiency or which one will get you better performance. It should be clear that the sequential should give you the least performance of the others because it has no concurrency whatsoever. Okay? The other three at least have concurrency in them. Okay? I already said process-based has more heavyweight context switching than thread-based. Better isolation, but if you're looking for performance, thread-based will have better performance because context switches are cheaper. For the same number of requests, you pay lesser tax of context switching. Is that clear? Okay. So clearly process-based is less efficient than thread-based. So that gets us to between event-based and thread-based, which is more efficient, which has better performance. Yes. Yeah, we'll get to that. So you're asking what about a mix where you can have processes and threads in them. We'll talk about that. I am asking right now, how do we compare thread-based and event-based, and we'll talk about the model you suggested. Yes. Can you use event-based and thread-based model? So that's another hybrid model. We'll get to that as well. For now, let's just compare these. Then we'll see how to mix them up. Okay. Yes. So actually, the answer is it depends on what kind of machine the server is running on. If you're single core, okay, event-based has to be better than thread-based because there's no context switching at all. Okay. Process-based has heavy context switching. This is lighter context switching. There's no context switching within the process. So this is the most efficient. So for very high performance servers, event-based is the way to go on a single core machine. Okay. If you have multi-core machine, thread-based will give you better performance because you can run multiple threads on multiple cores. You can do parallel processing, which event-based cannot do. Event-based will run on only one core at a time. Okay. This brings us to all these questions that were asked. Can you mix them up? Okay. So of course you can mix them up. You can do all kinds of hybrid models where you can have a thread-based server and each thread does event processing. So if you have, let's say, 4 cores, you start for 4-core server process. Each of those 4-threaded server process, excuse me, on the 4 cores, and each thread can do event processing on its core. Right? Request comes in, you give it to one of the 4 threads, and then those threads are essentially doing event processing. So it can serve multiple requests. Okay? That is an event-based threaded server, a mix. You can, of course, have a process-based architecture, but each process can also have multiple threads. So you can do all kinds of mix and match. It gets more complicated, but this is basically the progression of how you would do. Okay? Yes, question.
Event-based for the model in
Event-based model a programming paradigm, or is it given by hardware? No, that's how you are going to write the server. It's not a hardware thing. Okay? Hardware can give you interrupts and so on, but that's different from what we are talking. The event loop is simply event here is arrival of a request. Okay? So the event loop, what we talked about was at the very beginning. So that's our event loop. Okay? It's a while loop, an infinite while loop that's just waiting for request. That's the event. Okay? And you process the event, which is processed. So this you can think of it as a request loop also. Okay. All right. So there is one more model I just want to briefly mention, which was in the thread per request model. Okay. You can essentially have a variant of this, which is called a thread per connection or a thread per session model. Okay. So what happens in this case is when the client sends the first request, okay, that request is assigned to a thread. Okay. Normally, the process would the thread would process that request and then go back to being idle. Okay. And after it send the reply. Okay. But in a session-based model, we assume that the client has a session where it's sending a sequence of requests. Maybe it's a shopping application. You first pick a product, you put it in the cart, you buy it. So these are all requests that you are going to send to the server. So in this case, there's a single thread that's assigned for the entire session or the entire connection. Okay? While the connection is open, the socket connection is open, the thread continues to wait for new requests and process. Only when the connection is closed will the thread go back to the idle pool. Okay? So this is going to essentially say, I dedicate a thread to a client until the client has a connection open and is sending requests. You have the same thread. You don't wait for a request and give it another thread. Okay? So you'll keep that thread dedicated to that client. Okay? So this is called a thread per session, okay, or a thread per connection model. Okay? The reason I'm mentioning this is your lab is going to require you to write a simple multi-threaded server. Okay? And the way you need to write it for your first lab is go with the thread per request model. Don't do a thread per connection model, because that is not what we are asking you to do. We are asking you to do something very simple where the thread services a request, goes back to the idle pool, the client closes the connection. Client then opens a new connection for any new request. You do not keep the connection open. Okay, session-based things we'll look at later. Do the simple thing first. Okay, all right. So with that said, let's talk about. I just want to mention these the difference between the term parallelism and concurrency. I used both of these terms, okay, and we should understand that they are not the same. Okay, concurrency does not mean parallelism. Okay, concurrency simply enables the handling of multiple requests. Okay, so you essentially can do this with threads. You can do this with non-blocking calls. You can have concurrency on a single core. So you just essentially have the ability to handle multiple requests in your server. Parallelism says not only can you handle multiple requests, the processing of those requests can be parallelized. You can have multiple requests executing at the same time on different cores. Okay? So concurrency implies parallelism. But if you just have, parallelism implies concurrency. Okay? So parallelism, you should have concurrency. Okay, but the reverse is not. You can have concurrent servers that run on a single core. You're not going to get true parallelism. You'll never have a case where two requests are executing. There's only one core. You can't actually execute anything in parallel on one core. Okay, so understand the difference between these two terms. Okay, let's now talk about thread scheduling in whatever time we have left. So now let's talk. You now understand what are threads. We now understand how to write applications using threads. At least you saw several ways of writing a multi-threaded server, asynchronous servers, and so on. Let's now try to understand how an operating system is going to deal with threads underneath. How is it scheduling them? How does it decide which thread runs and all of that kind of stuff? Okay? That gets us to thread scheduling. So there are two models that we will look at as far as threads are concerned. Anytime your programming language gives you a threads package internally, it has to be implemented using one of two models. The one is called user level threads. The other is called kernel level threads. Okay. So a user level threads is a package where you have threading support, but the OS does not know about them. The OS does not manage them. Okay. Is the library that creates and creates this thread that manages them for you. Excuse me. So what are the advantages of user level threads? You don't need any OS support to implement threads. Okay? You can implement threads in user space using simple libraries without requiring any help from the operating system. If you have specifically, if you have an OS that does not have multi-threading support, which some OSs don't, okay, you can still have threads in your application and get all the benefits we talked about. Okay? So no kernel modifications needed to support threads. User level threads are very efficient, okay, as compared to the kernel level threads that we'll see, because creation, deletion of thread are library calls within that process. Okay? When you talk about kernel level threads, when you create a thread, that's a system call. The OS has to create the thread for you. Okay? In the user level threads, when you create a thread, the library in your process creates the thread for you. The OS doesn't know, the OS is not involved. Okay? So it's more efficient because creation, deletion switches are all more efficient. There is flexibility in scheduling because now you have to implement a thread scheduler in your library that's going to decide, should I execute my threads in round robin order or using some other technique. That is independent of the CPU scheduling processes. Okay? So you can choose a different scheduling technique inside your library to manage your user level threads, which is completely independent of what the OS is doing. So you can decide my application needs this type of scheduling, implement it in the library, and you have your own custom scheduler. Okay? Now, the disadvantages are because the OS does not know about the presence of threads, it thinks that this is a single threaded process because it doesn't know any better that there are threads in them. They're all being created by a library. OS cannot see them. Okay? So it thinks it's a single threaded process. So if any thread within that process makes a blocking call, the entire process is going to block because it thinks that that process has made a blocking call. It doesn't know that it was a specific thread within that process that made a blocking call. Is that clear what I said? So essentially all threads will block if any thread within that process makes a blocking call. Okay? And furthermore, if you have a user level threads package, you cannot have true parallelism, because even if you have multiple cores, the OS sees this as a single threaded process. Okay, inside it are multiple user level threads that the OS cannot see. So the OS cannot explicitly schedule 2 threads on 2 cores because it doesn't know they exist to begin with. Okay? So if any of user level threads, okay, you cannot get true parallelism because that process can be only scheduled on 1 core at a time, because you can't see the threads. You, as in the OS, cannot see them. Okay? So some things are better, some things are worse. Okay? And you can now think about the other. So here's an example of a user level thread before we do this. So these are your processors. Okay? So there are 2 cores. That's your operating system. There is a scheduler. Okay? And each of those boxes are essentially processes or address spaces. And these are the actual processes. So you will see the top process has 3 threads. There's a library scheduler that manages them. This process is also 3 threads. This process has 2 threads. Okay? The OS sees this as 3 single threaded processes. Okay? So it's going to, in this case, take this process, put it on this core. Okay? Once you do that, the library scheduler has to decide which of its threads actually runs. Okay? Because this, all this OS scheduler has done is said this process execute. It doesn't say which thread of that process executes. That decision is made by the library scheduler. So that's what I said. You can have whatever scheduler you want in there as independent of this one. Okay, so 2-level scheduling. OS runs the process. So library scheduler decides which thread within that process to run. Okay, and here is another scheduler. Another process that's running. So that scheduler decides which of these 2 execute. Okay. Now there will never be a case where this process is assigned 2 cores because it's seen as a single threaded process, even though it has multiple threads within it. Okay. Okay. Kernel level threads, exactly the opposite of everything we said. The OS is aware of the presence of threads. The OS explicitly supports threads. Thread creation, thread deletion require a system call. If the process says thread create, that's a system call. The OS actually creates the thread for that process. The OS allocates stack and all of that for that process. Okay? As a result, the OS can actually see how many threads are inside that process and explicitly schedule them. Okay? So in this case, scheduling is going to be more, the context switching overhead is going to be more than user level threads, because a context switch of threads requires a kernel level context. It's still cheaper than a process level switch, but it still involves the OS to do it for it. The library is not doing anything in this case. Okay? So that's harder. And furthermore, you are now bound by whatever CPU scheduler the OS has picked for you. So your threads are getting scheduled directly by the OS, not by some library that you have linked to your application. Okay? So you are essentially bound by the OS scheduler. Okay? So same example as before. You have your 3 processes, okay? And then you can see now that each of these threads is actually visible inside the OS. The OS can pick any of them to run. In particular, you see that it has chosen 2 of these to run at the same time. So this process is now getting true parallel execution, because 2 of its threads are running on 2 cores at the same time, which you would not have gotten in the previous case. Okay, yes, question. Yeah. The question is there a particular algorithm that the OS follows to pick threads? That is your CPU scheduling algorithm. Okay. I think the best way to think about this is whatever you learned in a undergrad class is the same scheduler. It could do round robin, you could do multi-level feedback queue, all of the standard ones. Whatever you use to schedule processes, that exact technique is now being used to schedule threads. Okay, so users don't get to choose. Now it's Windows and Mac that's doing this for you, right? So the OS decides. Whatever the OS developer has put in the OS, that's what is going to run. You can't check, say, I want round robin or anything like that, because the OS already has a scheduler. It will do what it has in it. Okay. Okay. So here's a quick example. Okay, then we are going to have 5 minutes left. So you will assume now what that the same question that was asked. Let's assume the CPU scheduler uses round robin. Okay, very simple scheduler. Okay, we'll look at some examples how it works. Okay, here's a program that has two functions. Okay, green function is called foo, the red one is called bar. Okay, if you have sequential execution, that's what it's going to look like. So first thing you have to remember, all CPU scheduler use the notion of a time slice. When it picks a process for execution, it gets to execute for up to a quantum, which is called a time slice. When the time slice expires, okay, the process has to yield, and then the CPU scheduler can decide to run some other process. Okay, in this case, that's only one process. Okay, so each of these small boxes is a time slice. So you finish the time slice, the OS scheduler says, what do I run next? There's only one process to run, so it gets to run. Okay, otherwise you would have switched back and forth with other processes. That's not happening here. So you will have 3 quantums where you run the green, and then you start executing the red one. Okay, because it's sequential execution. Okay, the x-axis here is time. Okay, so it's round robin, but there's nothing interesting happening yet. Okay, so now let's say foo and bar are in their own threads. Okay, so you have 2-threaded process. That program, the green is one thread and the red is another thread. Okay, so you have one time slice, you run the green one. The time slice expires. Okay, then you basically, because it's round robin, is going to run the other thread. Okay, so you have green and red, so you get interleaving. There's no parallelism yet, but you have interleaving. Both threads are making progress, even though there's one core and one processor. Okay, is this clear? Okay, so this is multi-threaded time slice scheduler. Okay, now let's say that there is some IO, okay, in that program. Okay, so and it is single threaded. Okay, we don't have so it's that program. You just have print statements in between. Okay, if it's single threaded, this is what is going to happen. So green will run as soon as it hits IO. It's going to, because it's blocking call, you block. So then essentially you are not going to run. Okay, the CPU scheduler may pick some other process to run, but if this is the only process in the system, the CPU will start idling because there's nothing else to run. Okay, so when you do IO, that's why there's nothing happening. So then IO finishes, you run the green again. The IO finishes, run the green again, and then the red. So there is essentially gaps in the execution of the process where the process is blocked for IO. Okay, this is what a blocking call will do. Okay, but that's single threaded. Okay, so what will happen if you make that multi-threaded? Okay, so here's what will happen. So let's say the green thread runs, it does IO, so the green thread is blocked. So then you go back to the CPU scheduler. The scheduler says, what do I run? There's a red thread that's still runnable, okay, because a multi-threaded process. Okay, so then while the green thread is doing IO, the red thread is going to run. Let's say it does IO, okay, and then the red thread will block. Okay, now if the previous IO hasn't finished, both threads are blocked at this point. Okay, so then nothing can run. But we assume that while the red thread is running, somehow that IO finished. That may or may not happen. But if it does finish, then you switch to the green thread. So you get perfect interleaving here. So while one thread is doing IO, the other one runs. Okay? So your CPU is continuously busy. It will not often happen because IO actually takes much longer than a time slice. So you may get gaps between these executions like you did there because both threads are doing IO. But if you get good interleaving, you essentially have, in this case, a perfect interleaving. Question is. Yes. Yes. So this is all kernel level threads. If you are user level threads, you wouldn't have gone this far. It would have looked like a sequential execution. Okay. So I mean, sorry, you would not have gone this far because the moment you did IO, the entire process would block. Right. So this is kernel level threads where you can switch. Otherwise, you would block at the first call. Okay. The last one is what happens if you have multiple cores. Okay. So here you have 2 cores. So you run the green one on one core, you run the red one on the other core. Okay. Both of them run, both of them start doing IO. In this case, both cores free up. If there's something else running in the system, they would run. Okay, because this is, we have assumed this is a toy example where this is the only process, both cores are idle. Okay, both of these do IO, and then both of them resume execute. Of course, they don't have to resume at the same time. That depends on how long the IO takes. But this is a toy example. So we say, okay, both run, then both do IO, both run, and so on. Okay, this is true parallelism with IO. Okay, so depending on the scheduler, what happens in the process and how it does IO, you will get different interleaving behavior. Is this clear? Any questions? Okay. 1 minute remaining. So I'm going to very quickly talk about scheduler activation, which is a way by which you can use user level threads, but somehow inform the kernel about the presence of other threads. So you don't block as soon as the first user level thread does blocking calls. As I said, that's a disadvantage of a user level threads library. The kernel doesn't know about their presence. So as soon as one thread blocks, the whole process. So I'm not going to go into all of these details, but the basic idea is the library scheduler works with the OS scheduler. Okay, the library scheduler informs the OS scheduler saying there are multiple threads within the process. So as soon as you see blocking call, don't block the whole process. There are other threads that can run. So that technique is called a scheduler activation. Okay? So you notify the user level threads of kernel, the event, the user level threads notifies the kernel about the presence of the multiple threads and so on. And there is information flowing back and forth that allows your user level threads to acquire similar properties as if they were kernel level, because you are now informing the OS about the presence of these threads. Okay? That's the basic idea. I don't have time to go into details because we ran out of time here. But the basic takeaway here is you can take user level threads libraries, have them cooperate with the operating system kernel, and then get some benefits of the kernel level threads that you had given up before. Okay? If you do that, you have something called scheduler activation. Okay? So we'll end it here today. Okay, remember that Monday is a holiday. There's no class. Okay. Next Wednesday is Monday schedule. So there is a class. It's going to be a guest lecture on sustainable computing. Okay. So make sure you come to it because it's still part of the course and still part of the test. It's not an optional lecture. Okay. So let's stop